Okay, part 2 of Friday. All right, let's move on to example number 2 and then 3. So, example 2, find the Thevenin and Norton equivalent circuits if the 2 ohm resistor represents the load resistance or circuit network number 2. So, represents the load is equivalent to the phrase as seen by, meaning the 2 ohm resistor should not be part of our analysis. Okay, the 2 ohm resistor should not be part of our analysis. So the first thing I would do is I would remove the 2 ohm resistor and redraw the circuit. Now, once I remove the 2 ohm resistor, what I have left in its place are open terminals. They are already labeled for us as A and B. I'm going to use the same convention. 12 ohms, 4 ohms, and 6 ohms. And this is 30 volts. Okay, so what I will have to do now is to determine the Thevenin equivalent circuit. I have to redraw this circuit 3 times. Once for Thevenin resistance, once for Thevenin voltage, and one more time for the Norton current. So again, drawing it 3 times. For 3 quantities. Okay, so for RTH, what do we need? For RTH, we need to replace all the independent sources in the circuit by reducing them to 0. All right, let's wait. 10-second pause. Let me know if you have any questions. Okay. So we had the original circuit. First step was to remove the 2 ohm resistor because of the problem statement. Once we remove the 2 ohm resistor, we have a circuit that looks like this between terminals A and B. We have to redraw 3 times to determine RTH, VTH, and Norton current, IN. So RTH requires that we replace the voltage source with a short circuit wire. And then we redraw the circuit. It would look like this. That's terminal A, terminal B, 6 ohms, and we wish to find REQ, the total equivalent resistance as seen from the perspective of the 2 ohm resistor. Voltage sources reduced to 0, meaning replaced with a short circuit wire. So we can see that our REQ. So the way you should present this as RTH, the Thevenin resistance, is equal to REQ between A and B. REQ should be shown labeled in the circuit diagram. Okay, show it and label it in the circuit diagram. And REQ would be 12 in parallel with 6 plus 4. Okay, 12 in parallel with 6 plus 4. So what do we get? 12 in parallel with 6 gives me 72 divided by 18 plus 4. Hence my REQ is 8 ohms. Hence, I can state RTH, Thevenin resistance, is 8 ohms. Let's take a pause. Let me write it down. Let me know if you have any questions. Any questions? Does this make sense so far? Okay. All right. Then I'm going to go move to the other side of the page, and I'm going to write VTH. Okay, what do we need for VTH? Nothing. VTH is simply determining the open circuit voltage between our analysis terminals. So in this case, we would draw out our circuit diagram. Let's make this a little bit larger. Okay. And $12 ohms, 4 ohms, 6 ohms, plus minus 30 volts. And this is A, this is B, this is plus minus VOC. Okay. That is the circuit diagram to determine the Thevenin voltage. So in the quiz or in an exam, if I ask you the question, draw out the circuit diagram to determine the Thevenin resistance, this procedure is what you must use on that particular circuit. Okay, you have the open terminals of analysis that you established at the beginning of your analysis, and then you take that circuit. Essentially, you would not have to modify it further. You simply take that circuit, note down and label the open circuit voltage VOC with a plus and a minus. Now, typically we assign plus at the top and minus at the bottom. But again, with any analysis, it does not really matter what you choose. Okay, it could turn out at the end of your analysis that VOC is negative, and all it would mean is that the actual reference sign is opposite. That's all it would mean. It wouldn't mean anything else. Okay, so how would we analyze this circuit? It's a relatively straightforward and simple circuit as far as we can see. right? You have 3 resistors, you have open circuit terminals. If this was, if you created this circuit in a lab, all you would do is you would measure the voltage between A and B using a multimeter, and that would be it. But manual analysis, let me show you something. Let's say the current coming from the source, is going down this pathway, right? Current for a source always goes from minus to plus. So it's going in the upwards direction. And according to our circuit diagram, would make a right turn and go through the 12 ohm resistor from the left. Now, when it gets to the junction, it should split. The question I would ask is there any current flowing through the 4 ohm resistor? Any current flowing through the 4 ohm resistor? Yes or no? The answer would be no, because current needs a pathway to flow, and the 4 ohm resistor is open. And here's the important concept. If the 4 ohm resistor is open, meaning it's not connected to anything at the other end, right? This terminal is open. And if it's open, there is no current flowing through the 4 ohm resistor, meaning there is no voltage drop across that 4 ohm resistor. If there is no voltage across the 4 ohm resistor, we can say, electrically speaking, these two nodes are exactly the same potential. So VOC is the voltage across the 6 ohm resistor. Voltage VOC is the voltage across the 6 ohm resistor. And that is the important concept. And I can redraw this circuit. Like this. A, B. This is the 12 ohm resistor. This is the 6 ohm resistor. This is the 4 ohm resistor. And because that 4 ohm resistor is hanging loose, it's not connected to anything at one end, we can state 12 and 6 are in series. A very important concept. So even though there is a third resistor connected at this node, that third resistor is effectively not part of the circuit because it is left hanging. And if that's the case, then the 4 ohm resistor may as well not be connected to the circuit. And we can say that the 12 and the 6 ohm resistors are in series. So if we wish to find the voltage across the 6 ohm resistor, we can directly apply voltage division. Let's take a 10-second pause while you think over all of that. Let me know if you have any questions. Okay, no questions. Then I can simply apply voltage division. And I can find out VOC as 30 times 6 divided by 12 plus 6. That gives me a value of 10 volts. And of course, VTH, what is going on? VTH is equal to VOC. So my Thevenin voltage is 10 volts. Okay, let's take a pause while you write it down. Let me know if you have any questions. All right, any questions? Let's move this to the left. Okay. That's from voltage division. If you wish to find, since 12 and 6 are in series, so the question being asked is, how is it 6 over 12 plus 6? The answer is because I'm applying voltage division. And voltage division means if I want to find the value of the voltage across the 6 ohm resistor, it's a fraction of the supply voltage divided by Req of that series connection. Req of the series connection is 12 plus 6, which is 18. And then, of course, that resistor itself is 6 ohms, so 6 divided by 18. That would be the fraction of the supply voltage 30. And of course, every circuit is different. So, this is a relatively straightforward and a smaller circuit, but it doesn't matter what kind of circuit it is. You can solve it using any method you choose. In this case, we were able to apply simple voltage division and solve it in one step. If it's a different kind of circuit, you would use a different analysis technique. Okay, shall we proceed? To find the Norton current, we would take our circuit and just copy this out from here. All right. So now we don't need VOC. What I need to do is I need to place a short circuit wire between the terminals A and B. And because we chose plus at the top and minus at the bottom, the current direction for ISC has to go from plus to minus. I'm going to label it as ISC here. Okay, so it's going from plus to minus. So from top to bottom, from A to B. So now, how has the circuit changed? So this circuit is different from the one we used for VTH, correct? There is a short in place between A and B. And whenever we do this, a circuit changes. So in this case, if we look at it, we see that the 4 ohm resistor is connected in parallel with the 6 ohm resistor. So the circuit has changed due to the short circuit wire that we have placed there. I can go ahead and I'm going to redraw the circuit in a way that will make sense. So let's do this. Okay. Then okay, so this is my 12 ohm resistor. This is, let's see, I can call this 6 and 4. Okay, so if I backtrack ISC, where is ISC coming from? ISC is the current that is flowing through the 4 ohm resistor, right? ISC is the current that is flowing through the 4 ohm resistor, meaning it's this current right here. I'll mark out terminals A and B. 4 ohm resistor. So this is B, and this is A. And ISC is flowing this way. Okay, techniques that come to mind. Again, I don't have to use any complicated analysis techniques. I can solve this using Ohm's law, KVL, KCL, or series parallel analysis. So this is what I'm going to do. I'm going to, let's see, let's call this voltage VZ. I'm going to combine the 6 and 4 ohm resistors in parallel to get 1 Req for that. So it's 24 divided by 10 gives me 2.4 ohms. From voltage division, I can write VZ is equal to 30 volts times 2.4 divided by 12 plus 2.4. Thus, I obtain a value for VZ as 5 volts. Let's take a pause while you write it down and let me know if you have any questions. Again, the analysis depends on how the circuit looks after you make the modifications. Yes. Okay. So we just look at 6 and 4. Okay. If you take a look at 6 and 4, doesn't matter which circuit diagram we look at, either this one or this one. We can see 6 and 4 are in parallel, right? So we can combine that together to get a Req of 2.4 for those two resistors. With me so far, right? So we got 2.4. Now, if we take a look at it, then we can state that 12 and the 2.4 are in series. So the 12 and 2.4 are in series. And if they're in series, I can apply voltage division to find the voltage. I can find the voltage across the 2.4 ohm resistor. To find the voltage across the 2.4 ohm resistor, by voltage division, that gives me a fraction of 30 volts, and the fraction, of course, is given by 2.4 divided by 12 plus 2.4. And that is how we obtain that last equation. Does that make sense? Okay. And then one more step would be apply Ohm's law, ISC. It would be 5 divided by 4, which gives me 1.25 amps. And hence, IN, which is equal to ISC, is also 1.25 amps. At this point, we will use Ohm's law to verify our answer. VTH should be equal to IN times RTH. IN is 1.25, RTH is 8, which gives me 10 volts, which is equal to VTH. So, thus my answer is verified. And this is what I will ask on the final exam. I'll ask you to go through the steps. I will ask you to draw out 3 circuits independently. I will ask you to do the analysis for each one of those 3 circuits and then verify your answer using Ohm's law. Again, Thevenin Norton guaranteed on the final exam. It'll be about a 30-point problem that will test everything from chapters 1 and 2. Job is not yet done. The actual final Thevenin circuit should look like this. So final Thevenin circuit and final Norton circuit. And again, this is also something I will ask in the exam. The final Thevenin circuit should look like this. Well, it will always look like this. A voltage source in series with a resistor, right? And then we connect R2 back into the circuit. And your final Norton circuit will always look like this. A current source in parallel with the Thevenin resistance. So RTH, 8 ohms. Current source should be going in the upwards direction. Okay. And the reason is our ISC is coming down in this direction. This is the 2 ohm resistor. So if the current source is not going in the upwards direction, then our ISC direction would not make any sense. If we obtain a minus value for the Thevenin voltage and the Norton current, then the voltage source and the current source should be flipped. Okay, those should be flipped. So this is VTH. VTH is 10 volts. This is RTH. RTH is 8 ohms. And then, of course, we have not R2, sorry, the 2 ohm resistor. This is IN, which is 1.25 amps. And again, as I said, this is what I would ask of you in the final exam. All right, let's take a pause, write it all down. Let me know if you have any questions. Any questions from anyone? Ready to move on to example 3? Yes. Nope. Oh, I mean, the final circuits? Okay, yeah, the question being asked is, would the final circuits always look like this? The answer is yes. The entire purpose of determining a Thevenin or Norton circuit is that we can represent any large linear circuit as a single voltage source or a single current source. Always will remain the same, yes. So the form of the final circuits will always remain the same. It'll always be like this. Well, actually, it would always be like this. Voltage source in series with a resistor. Because remember, sometimes the problem statement might be, analyze the circuit between A and B. There might not be a component connected there. But it doesn't really matter if there's a component connected, because that component will not be part of our analysis anyway. Right? So if the problem statement states, find the Thevenin circuit as seen by a particular resistor, then you remove that component from the analysis. So the final circuit is always a voltage source in series with the resistance. Norton is always a current source in parallel with that resistance. Always. So you can consider this as a freebie. It's going to be on the final exam. So if I asked you this, that's all a student has to do. Okay. You were asking something else? No, this is just the 2 ohm resistor that was present in the original circuit. Yeah, it was this resistor. Yeah. So again, if the 2 ohm resistor was not present, the question would have been, find the Thevenin circuit between A and B. Right? It would still be the same analysis. It would still be the same circuit. Nothing would change. Everything would remain the same. Okay. All right. Example 3. Find the Thevenin and Norton circuits if the 17 ohm resistor represents the load resistance. And again, represents the load resistance means the 17 ohm resistor is not part of our analysis. So as the absolute first step, we will remove the 17 ohm resistor, and we will redraw the circuit. I'm going to stretch out A, and then we have current source. So the difference here is that we have an attached current source at the top. This is A, this is B, plus minus 20 volts, 5 ohms, 10 ohms, and 20 ohms. And current source of 1.5 amps. So this is the first step, absolute first step always. Okay, so once we have done the initial first step, we have to redraw the circuit 3 times. Once for VTH, once for RTH. Actually, you know what? Let's draw RTH first. So RTH, VTH, and IN. So we redraw the circuit to find REQ. To find REQ, we reduce all independent sources to 0. Reducing a source to 0 means replacing a voltage source with a short circuit and replace the current source with an open circuit. Essentially just removing it from the analysis. So 5, 20, and 10. REQ, starting in the far left, is 5 parallel with 20, which is then in series with the 10. Gives me 100 divided by 25 plus 10, 14 ohms. 14 ohms. And RTH is equal to REQ, hence that is also 14 ohms. Okay, any questions? All right, let's see. Let's draw the circuit for VTH. VTH require I'm going to draw this a little bit larger. Ah. Okay. And the current source is going towards the right. 1.5 amps. Okay. This is A, this is B, and I need to find the open circuit voltage between those terminals. And the circuit is similar to the previous one with a big difference that there is an additional current source in the circuit. And if there's a current source in the circuit, well, whether it's a current source or voltage source, it doesn't matter. There are two sources in the circuit. So we cannot simply apply any simple analysis techniques. We have to solve this using node voltage analysis or mesh current analysis or superposition. You can use any analysis technique you want. Okay. So I'm going to choose node voltage analysis. And let's see how we can find VOC. So for node voltage analysis, I need to identify all the nodes. A and B are already given to us. I'm going to stick with those. I'm going to mark this node as C and this node here as D. Then I have to label all the branch currents. So I'm going to label this as, let's call this I1. Let's call this I2. Again, remember, these directions are arbitrary. I can select whatever direction I want. Okay. I'm just going by certain logic. Okay. I'll call this I3. And then, of course, I don't need to label anything up top. That is 1.5 amps. Now, 1.5 amps has nowhere else to go except here, because A is an open circuit. So let's mark out the other points also. I'm going to call this node as my reference. That entire node is basically B. And so you can write VB is equal to 0 volts. And therefore, VC is equal to 20 volts. So then I have only two unknowns left in the circuit, D and A. And that's all. So I'll take a pause. Let me know if you have any questions. Okay. If you look at VOC, VOC is connected between A and B. And for the purposes of this analysis, B is my reference. So if I wish to find the voltage at A, that would automatically turn into VOC. So I can write VOC is the voltage VAB, which, because B is my reference, is simply the node voltage VA. Okay. If I find node voltage VA, that would be my VOC, and that would be my Thevenin voltage. Okay. So the first thing I can write from here is that I3 is 1.5 amps, right? Because the 1.5 amp current source has nowhere else to go except through the 10 ohm resistor. Then I would apply KCL at D. KCL at D would give me two currents entering and two currents leaving. I can write I1 is entering, I3 is entering, I2 is leaving, and so is the 1.5 amp current source. But I3 is 1.5 cancels out. I can write I1 is equal to I2. Now I apply Ohm's law. I1 is the voltage across the 5 ohm resistor, V5 divided by 5, and I2 is V20 divided by 20. V5 can be written as VC minus VD divided by 5. And the 20 ohm resistor is VD minus VB divided by 20. So if I was to reduce this, I get 4 VC minus 4 VD is equal to VD. VB is 0, obviously. Cross multiply by 20 and 5 on both sides. Right? So now it's VC, 4VC minus 4VD. Therefore, wait, what did I, let's see, 20 and 5 divided by 4. Let's see, hold on. Oh, that's right, VC is 20 volts. So I get 5 times VD is 4 times 20. And therefore, VD is 80 divided by 5, which gives me 16 volts. Then to find A requires a couple more steps. Any questions so far? We found the voltage at node D right here. And node D with reference to B gives us 16 volts. 16 volts. Okay, I have about 10 minutes left, so I'm going to go a little bit faster, a little bit quicker. So we found VD is 16 volts, but actually I want to find VA, right? So let's see which equation can fit. I3. I3 is actually flowing through the 10 ohm resistor, which is connected between A and D. So if I write an expression for I3, I would be able to find VA. So let's see. I3 would be coming from the right. And so VA is higher than VD. So I can write I3 is equal to VA minus VD divided by the 10 ohm resistor. Plug in all the known values. I3 is 1.5. VD is 16. Therefore, VA is 1.5 times 10 plus 16. Therefore, VA is, actually, let's just write it here, 31 volts. And if VA is 31 volts, I can write VTH, which is equal to VOC, which is equal to VA is 31 volts. Okay. All right, any questions? what I'm going to do is I'm going to move on to the Norton current. About 8 minutes left. So I'm going to go a little bit faster. Okay, Norton current, IN. I would take the original circuit diagram, copy that over. Paste it here. Okay, so you don't need that. Wipe it out, wipe it out, wipe it out, wipe it out. The reason I'm wiping it out is because I'm going to use mesh current analysis to determine the current that is flowing from A to B. Now you can use node voltage analysis again if you wish, and that is absolutely fine. So for both, choose any one of those techniques, and it's absolutely fine. Okay, place a short circuit, and I'm going to use MCA, mesh current analysis. So if I use mesh current analysis, I'm going to identify 3 meshes right here. And I'm going to call them as I1, I2, and I3. Okay, this I3 is a mesh current. It's not the branch current. Okay, it's a big difference. This is mesh 1, this is mesh 2, and this is mesh 3. So I'm going to go through the solution. Let's see, how much time do I have left? 6 minutes. Okay, right off the bat, I can write out that I3, the mesh current I3, has a value of 1.5 amps. Then short circuit current has the value of the mesh current I2. So if you find I2, that would be it. We don't need to do anything else. Right. Generate equations by apply KVL. I would apply KVL in mesh 1. In mesh 1, I see 3 quantities. I have a voltage source, 20. Then I have voltage of the 5 ohm resistor and the voltage for the 20 ohm resistor. That should sum up to 0. Voltage source would have a minus. So solving this, I would get minus 20 plus I1 times 5 plus I1 minus I2 times 20 equals to 0. Solve this, I get 25 I1 minus 20 I2 is equal to 20. Thus, I can reduce it to 5 I1 minus 4 I2 is equal to 4. I'm going to call this and label it as equation number 1. Applying KVL in mesh 2, I obtain an expression V20 plus V10 is equal to 0. V20 is I2 minus I1. Note the change because I2 is the dominant current in mesh 2. And it's I2 minus I1 times 20 plus V10 would be I2 minus I3 times 10 equal to 0. So I would get minus 20I1 plus 20I2 plus 10I2 minus 10I3 is equal to 0. I3 already has a value of 1.5 amps. I can move that to the other side and I can write minus 20I1 plus 20I2, no, 30I2 is equal to 15. And I can call this as equation number 2. Okay, then I'm going to take equation number 1 multiplied by 4, and I would obtain, okay, take equation number 1 multiplied by 4, we'll obtain 20I1 minus 16I2 is equal to 16. Call this equation number 3. Equation number 2 plus equation number 3 gives me 14I2 is equal to 31. Therefore, I2 is equal to 2.2142 amps. And therefore, IN, my Norton current, which is my short circuit current, which is I2, is equal to 2.2142 amps. Verify with Ohm's law. IN times RTH is 2.2142 times 14, which comes out to be approximately 30.99 volts, which is my Thevenin voltage. Cash. Let's see. Okay. Your final Thevenin and final Norton circuit will look exactly the same as the previous ones. And so I can write final Thevenin circuit. (17 ohm resistor, RTH, VTH, and final Norton circuit should also look the same. This is A, this is B, this is A, this is B. 17 ohm, RTH, current source IN. Amps. RTH is 14 ohms, 14 ohms, and 31 volts. Okay, sorry for rushing through at the end. Do you wish me to scroll up? Okay. We can make this a little bit smaller. All right, we'll end class here today. We'll see you all on Monday. I'm bright and early at 10 o'clock for quiz number 4. Have a good weekend, and I'll be available over the weekend. If you have any questions, send me an email. If you wish to see me over Zoom, just let me know.